Welcome to Sleepy Cosmos Stories. I'm so glad you're here tonight. Before we begin, I'm curious, where are you right now? Are you in a quiet bedroom, nestled under soft blankets? Perhaps you're in a comfortable chair, the day finally winding down? Or maybe you're somewhere else entirely, just seeking a moment of peace. Wherever you are, I hope you're comfortable, safe, and ready to let your thoughts gently drift. If you enjoy these calming cosmic journeys and would like to hear more, a like or subscribe really helps this small channel continue. And to those already subscribed, thank you. Your support means more than you know. Tonight, we're not rushing anywhere. We're not solving complex equations or memorizing facts. We're simply wandering through the universe's quietest corners, its gentlest wonders, the peaceful secrets that stars, galaxies, and cosmic dust have been keeping for billions of years. I promise not to make this too interesting, just interesting enough to occupy your mind without keeping it awake, enough to remind you that you're part of something vast, beautiful, and remarkably calm. So, shall we begin? Take a deep breath and let's step into the quiet universe together. The patient journey of starlight. Right now, as you read these words, starlight is touching your skin. Not metaphorically, actually. Photons, tiny particles of light that began their journey thousands, sometimes millions of years ago, are ending that journey by gently landing on you, on your hand, your face, the wall beside you. Think about that for a moment. A photon is born inside a star, deep in the core, where hydrogen atoms are crushed together by immense pressure and heat. In that fusion, energy is released, and that energy becomes light. But it doesn't escape immediately. Inside the star, it's crowded, millions upon millions of atoms, all packed together. The photon tries to move outward, but every few millimeters it bumps into an electron, bounces, changes direction, bumps again. It's like trying to walk through an impossibly crowded room in complete darkness, bumping into every single person. For the photon, this journey from the star's core to its surface can take thousands of years, 10,000 years, 100,000, just to travel from the center to the edge. But eventually, it makes it. It reaches the surface, and suddenly, freedom. The photon shoots out into space at the speed of light, 300,000 kilometers per second. Fast, but the universe is vast. If that photon is coming from our sun, it takes just over 8 minutes to reach Earth. 8 minutes of silent travel through the vacuum of space. But if it's coming from a more distant star, say Sirius, the brightest star in our night sky, it takes 8.6 years. That light you see from Sirius tonight actually left the star in 2016. And if you're looking at even more distant stars, hundreds, thousands of years old, their light ancient. A message from the past arriving now for you. Some of the stars you see tonight might not even exist anymore. They may have died centuries ago, but their light is still traveling, still journeying, still finding its way to your eyes. There's something profoundly peaceful about that, isn't it? The universe is not rushed. Light takes its time, and when it finally arrives, after thousands of years of struggle and years of silent flight, it does so gently. It doesn't announce itself. It doesn't demand attention. It simply lands softly on your skin, in your eyes, and for a brief moment, you and a star separated by unimaginable distance and time, are connected. The sun's gentle hum, a star that sings. Our sun is not silent. If you could hear it, if sound could travel through the vacuum of space, the sun would hum. Not a roar, not a scream, a hum. Deep, resonant, constant, like the lowest note on an organ, held forever. This hum comes from the sun's interior. The star is not solid. It's a ball of plasma, superheated gas, constantly churning. Convection currents rise and fall. Hot plasma ascends, cools, and sinks back down, over and over. And as it moves, it creates vibrations. The entire star pulses, gently, rhythmically. Scientists call this helioseismology, the study of the sun's vibrations. By measuring these oscillations, they can peer inside the sun, understanding its structure, its temperature, its age. But set aside the science for a moment. Just imagine it. A massive ball of fire, 1.4 million kilometers wide, humming. A low, steady note that has been playing for 4.6 billion years, and will continue for billions more. If you are close enough to hear it, floating in a magical spaceship with sound somehow reaching you, it would be soothing, like standing next to a giant, warm engine, a heartbeat, a breath. The sun is not violent. Yes, it has flares, storms, explosions on its surface, but at its core, it is steady, patient. It has been burning the same fuel in the same way for nearly 5 billion years. Every second, the sun converts 600 million tons of hydrogen into helium, and in doing so, it releases energy, light, warmth. That warmth reaches Earth in just over 8 minutes, and it does so gently, not as a blast, but as a steady, reliable glow. Right now, even in the dark of night, the sun is shining. On the other side of the planet, it's day. People are waking up, feeling warmth on their faces. And tomorrow it will do the same for you, reliably, predictably, gently. There's comfort in that constancy, isn't there? The sun doesn't ask for anything. It doesn't demand recognition. It simply shines, day after day, year after year, for billions of years. And it will continue long after you and I are gone, long after humanity even. The sun humming its low, eternal note, patiently burning, quietly giving. Moons and their silent orbits. Let's talk about moons. Not our moon specifically, though we'll get there, but moons in general. These quiet companions orbiting their planets in the vastness of space. There are over 200 known moons in our solar system. Some are tiny, just a few kilometers across. Others are massive, larger than the planet Mercury. And they all share something remarkable. They orbit in near total silence. No friction, no air resistance, just the gentle pull of gravity keeping them in their endless dance. Take Io, one of Jupiter's moons. It's the most volcanically active body in the solar system. Its surface is constantly being reshaped by eruptions, lava flows, geysers of sulfur shooting hundreds of kilometers into space. But despite all that activity, Io's orbit is smooth, predictable. It circles Jupiter every 42.5 hours, has been for billions of years, and will continue for billions more. Or consider Enceladus, a small moon of Saturn. Beneath its icy surface lies a vast ocean of liquid water, and from cracks in the ice, geysers erupt, shooting water hundreds of kilometers into space. That water freezes instantly, forming tiny ice crystals that drift away, eventually becoming part of Saturn's E-ring. It's a quiet process, gentle, no explosions, no chaos, just water slowly escaping, becoming part of something larger. And then there's our moon. Every night it rises, sometimes full and bright, sometimes a delicate crescent, sometimes hidden entirely. But always, it's there, orbiting, slowly. The moon is gradually moving away from Earth, about 3.8 centimeters per year. Inch by inch, it drifts farther. Why? Tidal forces. The moon's gravity pulls on Earth's oceans, creating tides. And in return, Earth's gravity pulls back, ever so slightly, pushing the moon outward. It's been happening for billions of years, and will continue for billions more. One day, far, far in the future, the moon will be so far away that total solar eclipses will no longer be possible. The moon will appear too small to fully cover the sun. But that's okay. It's not a loss. It's just change. Slow, gentle, inevitable change. Right now, the moon is exactly where it needs to be, lighting up the night, pulling the tides, orbiting peacefully. And if you look up tonight, you might see it, a quiet companion, reflecting the sun's light, sharing it with you. No sound, no announcement, just presence.
Nebulae, clouds that birth stars. Deep in space, between the stars, there are clouds. Not like the clouds you see in Earth's sky. These clouds are vast, light years across, made of gas and dust so thin that if you were inside one, you wouldn't even notice. But over time, millions of years, these clouds do something remarkable. They collapse. Gravity pulls the gas and dust together, slowly, gently. Over eons, the cloud contracts. And as it contracts, it heats up. The center becomes denser, hotter, until one day, deep in the core, the temperature and pressure become so extreme that hydrogen atoms begin to fuse. A star is born. But this process is not violent, it's patient. Take the Orion Nebula, one of the closest star-forming regions to Earth. It's about 1,344 light-years away. And inside it, right now, stars are being born. But you can't see it happening in real time. It takes millions of years. From our perspective, the nebula looks still, frozen, a beautiful cloud of glowing gas, illuminated by young stars already formed. But in truth, it's active, churning, slowly giving birth to new suns. And when those stars finally ignite, they don't explode into existence. They gently begin to shine, first faintly, then brighter. Over thousands of years, they grow. Some nebulae are dark. They don't glow. They're called dark nebulae, and they block the light of stars behind them. The Horsehead Nebula is one of the most famous, a dark silhouette against a backdrop of glowing gas. It looks like a horse's head, rising from the cosmic landscape. It's peaceful, quiet, just a cloud of dust floating in space, patiently waiting. One day, it too will collapse, form stars, but not yet. For now, it simply exists, a shadow, a gentle reminder that not everything in the universe needs to shine to be beautiful. The slow rotation of planets. Planets spin, some fast, some slow, but all of them rotating on their axes, day after day, year after year. Earth completes one rotation every 24 hours. The day, familiar, comfortable. But not all planets are so quick. Venus, for example, rotates very slowly. One Venusian day lasts 243 Earth days. It takes Venus longer to spin once than it does to orbit the Sun. Imagine that, a day longer than a year. And even stranger, Venus rotates backwards, clockwise when viewed from above, the opposite direction of most planets. Why? No one knows for sure. Perhaps a massive collision in its early history knocked it off course. Or perhaps gravitational interactions with the Sun over billions of years gradually flipped it. Either way, Venus now spins slowly, gently, in its own unique direction. And then there's Mercury, the closest planet to the Sun. Mercury rotates once every 59 Earth days, and it orbits the Sun every 88 Earth days. Because of this unusual ratio, if you stood on Mercury's surface, you'd witness something strange. The Sun would rise, move partway across the sky, stop, reverse direction briefly, then continue forward again. A slow cosmic dance between rotation and orbit. But despite these oddities, there's something deeply calming about planetary rotation. It's reliable, predictable, governed by the laws of physics. No planet suddenly decides to spin faster or slower. They simply continue, steadily. Jupiter, the largest planet, rotates the fastest. One day lasts just under 10 hours. Despite its massive size, it spins quickly. But even that rapid spin is smooth, constant. The Great Red Spot, a storm larger than Earth, has been spinning for at least 400 years, probably much longer. And it continues, peacefully, a swirl of clouds rotating within a rotating planet. Everything in the universe is spinning. Galaxies, stars, planets, moons, asteroids. Spin is fundamental, and in that spin there's rhythm, predictability, peace.
Cosmic dust, the universe's smallest travelers. Let's talk about dust. Not the dust on your furniture. Cosmic dust. Tiny particles, smaller than grains of sand, some as small as smoke particles. They float through space, alone, silent, traveling for millions, sometimes billions of years. Where do they come from? Some are born in the atmospheres of dying stars. As red giants shed their outer layers, they release dust into space. Some come from asteroids. When two asteroids collide, they shatter, creating countless tiny fragments. Some are even older, grains of dust that existed before our sun formed, pre-solar grains preserved in meteorites, ancient beyond imagination. And these tiny specks drift slowly through the vast emptiness. Sometimes they encounter a planet, Earth, for example. Every day, about 100 tons of cosmic dust gently falls onto Earth, silently, unnoticed. It settles on mountains, oceans, cities, forests. Right now, there's cosmic dust on you, in your hair, on your skin, particles that traveled through space, perhaps for millions of years, and ended their journey by landing on you. And that's beautiful, isn't it? You're not separate from space. You're part of it, constantly being touched by the cosmos. Some of this dust becomes part of Earth. It settles into the soil, gets absorbed by plants, enters the food chain. So, in a very real way, you're made of cosmic dust, not metaphorically, literally. The calcium in your bones, the iron in your blood, the carbon in your cells, all of it came from stars that died long ago, exploded, scattered their elements into space, and those elements drifted as dust for eons, until they found their way here, to Earth, to life, to you. So when you look up at the stars, you're not just looking at distant lights, you're looking at your ancestors, the ancient furnaces that forged the atoms in your body. And they're still out there, still making dust, still sending it drifting through the cosmos, quietly, patiently, gently.
The Milky Way's gentle rotation. Right now, you're moving, not just because Earth is spinning, not just because Earth is orbiting the sun. You're moving because the entire solar system, sun, planets, and all, is orbiting the center of the Milky Way galaxy at about 828,000 kilometers per hour. That sounds fast, doesn't it? Almost violent. But here's the thing. The galaxy is so vast that even at this speed, it takes our solar system about 225 million years to complete one orbit. 225 million years. One galactic year. The last time we were at this exact point in the galaxy's rotation, dinosaurs hadn't evolved yet. The continents looked completely different. Life on Earth was still mostly in the oceans. And we're only a tiny fraction through our current orbit. We won't return to this spot for another 225 million years. That's how slowly the galaxy turns. From our perspective, the stars around us seem fixed. Constellations remain the same throughout our lifetimes. The Big Dipper, Orion, the Southern Cross. They look eternal, unchanging, but they're not. They're moving too, orbiting the galactic center just like us. Some a little faster, some a little slower. Over tens of thousands of years, the constellations we know will drift apart, slowly, gently. New patterns will form. But for now, tonight, they're exactly where they've always been in your lifetime. Familiar, comforting, steady. The Milky Way itself is a barred spiral galaxy. From above, it would look like a giant pinwheel with graceful spiral arms curving outward from a central bar of stars. Those arms aren't solid. They're density waves, regions where stars, gas, and dust are slightly more concentrated. As the galaxy rotates, these waves remain relatively stationary while stars pass through them, like cars slowing down as they pass through a crowded section of highway, then speeding up again. And in those spiral arms, where gas and dust are compressed, new stars are born. Nebulae light up. Young, hot blue stars shine brightly. But even this process is slow, gentle. Stars aren't popping into existence every second. It takes millions of years. The Milky Way is not in a rush. It has been rotating for over 13 billion years, and it will continue for billions more. Right now, as you lie here, you're part of that rotation, carried along by the galaxy's gentle spin. You can't feel it, but it's happening. And there's something deeply peaceful about that, isn't there? To know that you're moving through space, part of a galaxy's ancient, patient dance. Galaxies colliding in slow motion. Galaxies don't stay isolated forever. Gravity pulls them together, and sometimes they collide. But when you hear collision, you might imagine something violent, explosions, chaos, destruction. It's not like that. Galactic collisions are slow, gentle, beautiful. Take Andromeda, our nearest large galactic neighbor. It's about 2.5 million light-years away, and it's coming toward us. In about 4.5 billion years, Andromeda and the Milky Way will collide. But collide is a misleading word because galaxies are mostly empty space. Stars are so far apart that when two galaxies merge, individual stars almost never actually hit each other. They just pass by. Imagine two swarms of fireflies drifting through each other on the summer night. The fireflies don't collide. They simply intermingle. Some get closer, some drift farther apart, but the swarms merge smoothly. That's what will happen to our galaxy and Andromeda. The process will take hundreds of millions of years. Slowly, the two spirals will distort. Gravitational forces will stretch them, pull out long tails of stars. Eventually, they'll merge into a single, larger galaxy, probably an elliptical galaxy, a smooth, rugby ball-shaped collection of stars with no distinct spiral arms. And during all of this, on Earth, if Earth still exists, the night sky will change. Gradually, over millions of years, new stars will appear. Some stars will seem to drift. Andromeda, which currently looks like a faint smudge in the sky, will grow larger, brighter, until one day it fills the sky, not as a threat, as a companion, a beautiful neighbor finally arriving for a slow cosmic embrace. Some stars from Andromeda will become part of our sky. Some of our stars will join theirs. And in the end, a new galaxy will be born, stable, peaceful, rotating gently, just as the Milky Way and Andromeda do now. Astronomers have already witnessed many galactic mergers. They've taken pictures of galaxies in various stages of collision. Some are just beginning to interact, spiral arms reaching out, barely touching. Others are deep in the process, distorted, stretched, streams of stars connecting them like bridges. And some have finished, smooth elliptical galaxies, now settled into their new form, calm, as if nothing dramatic ever happened. Because to the galaxy, nothing dramatic did happen. It was just another slow dance, another inevitable step in the cosmic rhythm. Galaxies merge, and in doing so, they don't destroy, they create.
Gravitational waves, ripples in the fabric of space. Space is not empty. It's not a void. It's a fabric, a flexible structure that can bend, stretch, and ripple. Einstein called it space-time, and when massive objects move, especially when they accelerate or collide, they create waves in this fabric, gravitational waves. Imagine dropping a pebble into a still pond. Ripples spread outward, gently disturbing the water's surface. Gravitational waves are similar, but instead of water, they ripple through space-time itself. In 2015, scientists detected gravitational waves for the first time. Two black holes, each about 30 times the mass of the Sun, had collided 1.3 billion light-years away. As they spiraled toward each other, they moved faster and faster, and in their final moments, they merged. That merger released a tremendous amount of energy, more than all the stars in the observable universe combined, for a brief instant. But that energy wasn't released as light or heat. It was released as gravitational waves, and those waves spread outward at the speed of light in all directions. For 1.3 billion years, they traveled through space, undisturbed, silent, passing through galaxies, through nebulae, through empty voids, until on September 14, 2015, they reached Earth. And in that moment, space-time itself stretched and compressed, just a tiny bit, less than the width of a proton. But sensitive detectors called LIGO felt it, measured it, recorded it. And for the first time, humanity heard the universe in a new way. Because gravitational waves can be converted into sound. And when scientists did that, they heard a chirp, a rising tone, lasting less than a second. The sound of two black holes merging 1.3 billion years ago, finally reaching us. Since then, dozens more gravitational wave events have been detected. Black hole mergers, neutron star collisions. Each one a ripple, a gentle disturbance in space-time. And here's the beautiful part. Those ripples are still traveling. Right now, gravitational waves from countless cosmic events are passing through you. You can't feel them, they're too small, but they're there. The fabric of space around you is constantly being gently stretched and compressed by distant collisions, mergers, and explosions. You're being touched by the universe in the most subtle, gentle way possible. And those waves will keep traveling
forever, spreading outward, growing weaker, but never truly disappearing. Long after the black holes have evaporated, long after the galaxies have merged, the waves will still be there, faint echoes of ancient events, quietly rippling through the cosmos. Black holes, not destroyers, but sculptors. Black holes have a reputation: monsters, devourers, cosmic vacuum cleaners that suck in everything nearby. But that's not quite right. Yes, black holes have immense gravity. Yes, if you get too close, you can't escape. But they don't roam around hunting for things to consume. They're not aggressive. They're more like anchors. At the center of most galaxies, including our own, sits a supermassive black hole. In the Milky Way, it's called Sagittarius A star, pronounced Sagittarius A star. It has a mass of about 4 million suns, and it sits there, quietly, at the galactic center. Stars orbit around it, some very closely. Astronomers have tracked individual stars zipping around Sagittarius A star, completing orbits in just 16 years. That's fast for a star. But the black hole doesn't pull them in. It just holds them in orbit, like the sun holds Earth. Occasionally, a star gets too close. And yes, in those rare cases, the black hole's tidal forces can tear the star apart, shred it, consume it. But that's rare. Most stars keep their distance, orbiting peacefully for billions of years. And in a way, the black hole is what holds the galaxy together. Its gravity helps keep the stars in their orbits, prevents them from drifting away. Without it, the galaxy might not have formed the way it did. The black hole is a sculptor, shaping the galaxy's structure, influencing the flow of gas and dust. Even the jets that some black holes produce, enormous beams of particles shooting out at nearly the speed of light, are not destructive. They're creative. Those jets carry energy far into space. They heat surrounding gas, prevent it from cooling and collapsing. In doing so, they regulate star formation. Too many stars forming at once would deplete a galaxy's gas reserves too quickly. The black hole's jets slow things down, pace the process. In a way, black holes are gardeners, pruning, shaping, ensuring the garden doesn't grow wild. And most of the time, they're quiet. Sagittarius A star, despite being 4 million times more massive than the Sun, is relatively inactive. It's not currently feeding on much material. It just sits there, a dark, silent anchor at the heart of our galaxy. And stars orbit around it, peacefully, year after year, eon after eon. One day, billions of years from now, our Sun might drift closer to the galactic center, perhaps even close to Sagittarius A star. But even then, it's unlikely to be consumed. More likely, it'll just swing past, influenced by the black hole's gravity, but not destroyed. Just another quiet encounter in the long life of the galaxy.
Calm and slow. The cosmic web, a universe connected. Zoom out, far out, beyond galaxies, beyond galaxy clusters. Look at the universe on its largest scale. What do you see? Not randomness, structure. Galaxies aren't scattered evenly through space. They cluster together, form groups. Those groups form superclusters, and those superclusters are connected by filaments. Long, thread-like structures made of dark matter, gas, and galaxies. And between those filaments, voids, huge empty regions where almost nothing exists. Together, this forms the cosmic web. It looks organic, like neurons in a brain, or like a sponge, threads of matter surrounding empty bubbles. And it's all connected.
A galaxy in one filament is linked through gravity to galaxies in another filament across hundreds of millions of light years. This structure formed over billions of years, slowly, gently. In the early universe, matter was almost, but not quite, evenly distributed. Tiny fluctuations, regions slightly denser than others, and gravity amplified those fluctuations. Dense regions attracted more matter, became denser, while sparse regions became emptier. Over time, this created the web, and galaxies formed along the densest threads where matter was most concentrated. Our Milky Way sits in a filament, part of a structure called the Laniakea supercluster, which contains about 100,000 galaxies. And Laniakea itself is just one small part of the cosmic web. The web is not static, it's slowly evolving. Filaments grow, voids expand, galaxies drift along the threads like droplets of water on a spider's web. But the changes are so slow, over hundreds of millions of years. From our perspective, the web looks frozen, eternal. And there's something deeply peaceful about that structure. Everything is connected. Every galaxy, no matter how isolated it seems, is part of a larger whole. You, on Earth, in the Milky Way, are part of that web, part of a cosmic network that spans the observable universe. Not alone, not adrift, connected. But let's talk about the spaces between, the voids. These are the largest empty regions in the universe, hundreds of millions of light years across. Inside a void, there are almost no galaxies, almost no stars, almost nothing. Just space. Dark, silent, still. If you could somehow exist inside a void, what would you see? Almost nothing. No nearby stars, no galaxies on the horizon, just a few faint smudges of light, incredibly distant. The cosmic microwave background, the faint glow of the Big Bang, would still be there, but other than that, darkness. It would be the most isolated place in the universe. And yet even voids aren't truly empty. There's still dark matter, dark energy, the fabric of space-time itself. And occasionally a lone galaxy, a wanderer, somehow ending up in the void. These void galaxies are rare, and they're unusual because they formed in isolation. They often look different from galaxies in denser regions, less disturbed, more symmetrical, quietly evolving on their own. In a way, voids are the universe's quiet rooms, places where the cosmos rests, where nothing much happens. And they're expanding. As the universe expands, voids grow larger, filaments stretch, galaxies drift farther apart. One day, trillions of years from now, the voids will dominate. Galaxies will be so far apart that from any one galaxy you wouldn't be able to see any others. Each galaxy alone in an expanding void, isolated, silent. But that's far in the future. For now, the voids are just peaceful pockets of emptiness, reminders that the universe doesn't need to be full of stars to be beautiful. Sometimes emptiness itself is enough.
Calm and slow. Pulsars, the universe's most reliable clocks. Let's return to something smaller, but no less fascinating. Pulsars. These are neutron stars, the collapsed cores of massive stars that spin fast, very fast. Some pulsars rotate hundreds of times per second. And as they spin, they emit beams of radiation from their magnetic poles, like a lighthouse.
If Earth happens to be in the path of that beam, we see a pulse, a flash, every time the pulsar rotates. Hence the name, pulsar, pulsating star. But here's the remarkable thing. Pulsars are incredibly regular. Some pulsars are so precise that they rival atomic clocks. They pulse at the exact same rate, over and over for years, decades, millennia. Astronomers use them as cosmic timekeepers. In fact, some spacecraft, like Voyager, use pulsars for navigation. By measuring the timing of pulsar signals, a spacecraft can determine its position in the galaxy. It's like using lighthouses to navigate at sea, except these lighthouses are neutron stars, scattered across the galaxy, flashing with perfect regularity. And despite their speed, there's something deeply calming about pulsars. They're dependable, steady, unchanging. In a universe where so much is chaotic and unpredictable, pulsars are anchors of reliability. One of the most famous pulsars is PSR 1919 plus 21. It was the first pulsar ever discovered in 1967 by Jocelyn Bell Burnell. When she first detected its signal, a regular pulse every 1.337 seconds, she and her colleagues briefly wondered if it might be a signal from an alien civilization. They even jokingly called it LGM-1 for Little Green Men. But soon they found more pulsars and realized these were natural phenomena, spinning neutron stars, not alien beacons. Though in a way they are beacons, cosmic lighthouses, guiding us, keeping time. And they'll continue for millions of years, slowly spinning down, but never stopping abruptly. A pulsar is the ultimate symbol of patience, born in a violent supernova, yes, but now quietly spinning, flashing, keeping time. For eons. Right now, the most powerful telescopes are looking back in time, not metaphorically, actually. When you look at a distant galaxy, you're not seeing it as it is now. You're seeing it as it was when its light left. The farther away something is, the longer its light takes to reach us, and the farther back in time we're looking. Some galaxies are so distant that their light has been traveling for over 13 billion years. The universe itself is only 13.8 billion years old. So when we see these galaxies, we're seeing them as they were when the universe was young, just a few 100 million years after the Big Bang. These are the first galaxies, the pioneers. Small, irregular, chaotic, not like the grand spirals we see today. And their light is incredibly faint. By the time it reaches us, it's been stretched by the expansion of the universe, redshifted. The wavelengths lengthened. What was once visible light is now infrared. The James Webb Space Telescope was designed specifically to see this ancient light, to peer back to the cosmic dawn. And what it's found is breathtaking. Tiny, glowing smudges, galaxies that existed when the universe was less than 5% of its current age. They don't look like much, no grand spiral arms, no majestic structure. Just small clumps of stars, blue and hot, furiously forming new suns. But they're precious because they're the ancestors of everything we see today. Our Milky Way, Andromeda,
Every galaxy in the observable universe, they all descended from small galaxies like these. Over billions of years, those early galaxies merged, grew, became the giants we see now. But back then, they were just beginning, small, fragile, glowing faintly in the darkness. And their light has been traveling ever since, for 13 billion years, crossing unimaginable distances, just to reach us tonight. When astronomers capture an image of one of these galaxies, they're seeing light that has been journeying since before Earth existed, before the sun formed, before most of the atoms in your body were created. And yet that light is still here, still arriving, gently, quietly. It doesn't announce itself. It's so faint that it took billions of dollars of technology and years of careful observation to detect it. But it's there, a whisper from the universe's childhood, still traveling, still reaching out. And in a way, it's a message, a reminder that even the faintest light can endure, can cross the vastness of space and time, and arrive, finally, to tell its story. Brown dwarfs, stars that never quite ignited. Not every star makes it. Most clouds of gas and dust that collapse under gravity become stars. The core heats up, hydrogen fusion begins, a star is born. But sometimes there isn't quite enough mass. The cloud collapses, it heats up, but not enough. The core never reaches the temperature needed for hydrogen fusion, and what you get is a brown dwarf. Not quite a star, not quite a planet, something in between. Brown dwarfs glow, but very faintly, and not from fusion, from leftover heat, the warmth of their formation slowly radiating away. Over billions of years, they cool, dim. Eventually, they'll become cold and dark, but for now, they emit a soft infrared glow, invisible to the naked eye, but detectable with the right instruments. There are billions of brown dwarfs in our galaxy, maybe more brown dwarfs than actual stars, but we've only discovered a few thousand because they're so faint, so hard to see. Imagine that, an entire population of almost stars quietly glowing in the darkness, unnoticed, unremarked upon. They don't power planets, they don't create light for life. They simply exist, gently cooling, fading slowly into the cosmic background. And there's something peaceful about that, isn't there? Not everything needs to shine brightly. Not everything needs to be a sun. Brown dwarfs are content to be what they are. Warm embers, quiet presences, slowly, patiently cooling over timescales longer than the current age of the universe. Some brown dwarfs are very young, still relatively warm, glowing a dull red. Others are ancient, cool, dark brown or even black, barely radiating at all. And eventually, billions of years from now, they'll be completely cold, black dwarfs, invisible. But they'll still be there, still existing, silent witnesses to the passage of time. In a way, brown dwarfs are the universe's introverts. They don't seek attention. They don't demand to be noticed. They just are. And that's enough.
White dwarfs, the slow fade of stellar remnants. When a star like our sun dies, it doesn't explode. It swells into a red giant, sheds its outer layers, and what remains is the core, hot, dense, but no longer fusing hydrogen, a white dwarf. It's about the size of Earth, but with the mass of the sun, incredibly dense. A teaspoon of white dwarf material would weigh as much as an elephant, and it glows, bright white at first, hence the name. But there's no fuel left, no fusion happening. It's just hot, radiating the leftover heat from its previous life as a star. And slowly, over billions of years, it cools. The white dwarf fades from white to yellow, from yellow to red, from red to dim infrared. Eventually, after tens of billions of years, it becomes a black dwarf, a cold, dark cinder, no longer glowing at all. But the universe isn't old enough for that yet. No black dwarfs exist. Every white dwarf is still cooling, still glowing, even if faintly. Our sun will become a white dwarf one day, about 5 billion years from now. It will swell, engulf Mercury, probably Venus, maybe even Earth. Then it will shed its outer layers. A beautiful planetary nebula will form around it, glowing gas lit by the hot core at its center. And that core, our sun's core, will become a white dwarf. For a while, it will be bright, shining with the heat of its former nuclear furnace, but with no new energy being created, it will cool, dim. In 1 billion years, it will be yellow. In 10 billion, orange. In 20 billion, a dull red. And it will continue, fading, cooling, for trillions of years. But even as it fades, it will still exist, a monument, a remnant of what once was. And if any planets survive, if Earth somehow escapes being consumed, they'll orbit this white dwarf in the dim, cold light of a dying star. It won't be warm, it won't sustain life, but it will be there, a gentle glow in the darkness. And perhaps, in that distant future, that faint light will be enough to remember, enough to honor what the sun once was. Right now, there are billions of white dwarfs in our galaxy, most of them ancient, cooling quietly. Some are so old they've cooled to the point where their outer layers have crystallized, turned into a form of carbon, essentially diamond. Giant, slowly cooling diamonds floating in space. They don't shine brightly, they don't draw attention, but they're there, patient, enduring. The universe's longest-lasting lights, embers that will glow, however faintly, for longer than stars like our sun will even exist. Red dwarfs, the stars that will outlive everything. If white dwarfs are the longest-lasting embers, red dwarfs are the longest burning flames. Red dwarfs are small stars, the smallest true stars, just barely massive enough to sustain hydrogen fusion. They're dim, cool, reddish in color. Our sun is not a red dwarf. It's a medium-sized yellow star, and it will burn for about 10 billion years total. But red dwarfs? They burn for trillions of years. Why? Because they're so small, they burn their fuel incredibly slowly. A red dwarf uses its hydrogen so efficiently that even the smallest red dwarf will outlive our sun by a factor of 100 or more. Some red dwarfs will burn for 10 trillion years, 20 trillion, longer than the current age of the universe by a factor of 1,000. And even after they've exhausted their hydrogen, they won't explode. They'll just fade, slowly transition into white dwarfs. But that won't happen for an unimaginably long time. Right now, every red dwarf that has ever formed is still burning. None have died yet. The universe simply isn't old enough. In fact, the longest-lived red dwarfs are just getting started. They've barely used any of their fuel. They have trillions of years ahead of them. And they'll still be shining long after our sun is gone, long after most galaxies have merged, long after the universe has changed in ways we can't imagine. Red dwarfs are the universe's marathon runners, slow, steady, enduring. They don't shine brightly. Most of them are too dim to see with the naked eye, even if they're relatively close. Proxima Centauri, the closest star to our sun, is a red dwarf. It's only 4.24 light-years away, and yet you can't see it without a telescope. It's too faint. But it's there, burning quietly, patiently, and it will continue long after humanity is gone. Red dwarfs are the ultimate survivors, the final stars. In the far, far future, trillions of years from now, when all the massive stars have died, when the universe is cold and dark, red dwarfs will still be burning. Faint, lonely lights in an otherwise empty cosmos. The last embers, the final witnesses. And eventually, even they will fade, One by one, they'll exhaust their fuel, become white dwarfs, cool, darken, and the universe will enter an age with no stars at all, just remnants, cooling, fading. But for now, red dwarfs are still burning, quietly, reliably, a promise that even in the dimmest light, there is endurance.
The afterglow of creation, the cosmic microwave background. Now let's talk about the faintest light of all, the cosmic microwave background. This is the afterglow of the Big Bang itself, the oldest light in the universe. About 380,000 years after the Big Bang, the universe cooled enough for atoms to form. Before that, it was too hot, just a soup of charged particles and photons. But once atoms formed, light could finally travel freely. And it did, in all directions. That light has been traveling ever since, for over 13 billion years. But as the universe expanded, the light was stretched, redshifted. What was once visible light is now microwave radiation. Faint, cold, just 2.7 degrees above absolute zero. But it's everywhere, filling all of space, a faint, uniform glow. If you could see microwaves, the entire sky would glow, not brightly, just a soft, even luminescence in every direction. This is the cosmic microwave background, or CMB, and it's the oldest thing we can see. Every photon in the CMB has been traveling since the universe was 380,000 years old, long before galaxies formed, before stars, before planets. And those photons are still here, gently bathing the universe in their ancient light. Scientists have mapped the CMB in incredible detail, and it's almost perfectly uniform, almost the same temperature in every direction. But not quite. There are tiny fluctuations, regions that are slightly warmer or cooler by just a few millionths of a degree. And those tiny fluctuations, they're the seeds of everything. Galaxies formed in the slightly denser regions where the CMB was slightly warmer. Over billions of years, gravity amplified those tiny differences, and the cosmic web emerged. So in a way, the CMB is a baby picture of the universe, a snapshot from when it was just beginning. And that light is still here, still reaching us, quietly, constantly. Right now, CMB photons are passing through you, trillions of them every second. You can't see them, can't feel them, but they're there. Ancient light from the dawn of time, still traveling, still glowing. If you've ever seen static on an old TV, back when TVs had antennas, about 1% of that static was actually the CMB, the afterglow of the Big Bang picked up by your antenna. You were seeing the oldest light in the universe mixed in with random noise. Isn't that remarkable? The faintest glow, the quietest whisper, and it's been traveling for over 13 billion years just to reach you. And it will continue, forever. As the universe expands, the CMB will stretch further, cool further, but it will never disappear. It's woven into the fabric of space itself, the universe's eternal nightlight, faint, but always there.
Rogue planets, silent wanderers in the dark. Not all planets orbit stars. Some drift alone, through the darkness, unbound, untethered. These are rogue planets. They were likely ejected from their solar systems. Perhaps a gravitational interaction with another planet kicked them out, or their star died and they were flung into space. Now they wander, alone, in the cold, in the dark. No sunlight, no warmth from a nearby star, just the faint heat of their formation slowly radiating away. And perhaps, if they're massive enough, a little warmth from radioactive decay in their cores. But mostly, they're cold, dark, silent. It's estimated there could be billions, perhaps trillions of rogue planets in our galaxy. More rogue planets than stars. But we've only detected a handful because they don't shine, they don't reflect light, they're nearly invisible. Occasionally, one passes in front of a distant star, and for a brief moment, its gravity bends the star's light, a technique called gravitational microlensing. That's how we find them, by their shadows, by the way they distort light. But otherwise, they're ghosts, drifting silently through the void. Some rogue planets might have moons, and if those moons are geologically active, they might have subsurface oceans, kept liquid by tidal heating. Could there be life on a rogue planet's moon, in a dark ocean far from any star? We don't know, but it's possible. Life that evolved in total darkness, never seeing a sun, never knowing day or night, just the steady, gentle warmth of a moon's core and the silent, eternal night of interstellar space. It's a lonely thought, but also strangely peaceful. A world untouched by the chaos of a solar system, no asteroid impacts from nearby debris, no stellar flares, no solar wind, just stillness, silence, slow, cold wandering through the galaxy. And perhaps, in that isolation, a kind of peace. Rogue planets remind us, not everything in the universe needs to orbit something. Not everything needs a center. Some things just drift, alone, quietly, and that's okay. Neutrino emissions, the universe's invisible messengers. Finally, let's talk about something you can't see at all: neutrinos. These are subatomic particles, almost massless, barely interacting with anything. Right now, trillions of neutrinos are passing through your body every second, from the sun, from distant supernovae, from cosmic rays hitting Earth's atmosphere. They pass through the Earth itself, through buildings, through you. Almost nothing stops them. Occasionally, very rarely, a neutrino will interact with an atom, and when it does, scientists can detect it. Deep underground, in massive tanks of water or ice, detectors wait, hoping to catch a neutrino. And every so often, they do. A flash of light, a tiny signal, proof that a neutrino, born in the heart of the sun or in a distant exploding star, interacted just once. Neutrinos are the universe's most elusive messengers. They carry information from places light can't reach, from the cores of stars, from the moments after the Big Bang. There's even a cosmic neutrino background, like the CMB, but made of neutrinos instead of photons. These neutrinos were created just seconds after the Big Bang, and they're still here, filling the universe. But they're even harder to detect than the CMB, so faint, so elusive. We've never directly detected them, but we know they're there. Theory predicts it, and one day, technology might catch up. Until then, they remain the universe's quietest whisper, invisible, intangible, but everywhere. Right now, ancient neutrinos from the Big Bang are passing through you, carrying secrets from the universe's first moments. You'll never feel them, never see them, but they're there. Silent travelers, eternal wanderers. The universe's way of reminding us, not everything that exists needs to be seen.
Right now, Earth is moving. You're sitting still, or lying still, but you're actually traveling at about 107,000 kilometers per hour. That's how fast Earth orbits the sun. And you don't feel it, not even slightly. Why? Because the motion is smooth, constant. There's no acceleration, no sudden changes, just a gentle, continuous glide through space. Earth has been doing this for 4.5 billion years, circling the sun over and over. 365.25 days per orbit, give or take a few hours. Utterly reliable, utterly predictable. And it happens in silence. No friction, no air resistance, just the pull of the sun's gravity keeping Earth in its path. The same is true for every planet in our solar system. Mercury,
closest to the Sun, completes an orbit in just 88 days. It moves faster, about 170,000 kilometers per hour, but just as silently. Neptune, the farthest planet, takes 165 Earth years to complete one orbit. Slow and steady, patient. Each planet follows its own path, its own rhythm, and they all do it together, a solar system-wide dance, choreographed by gravity. The orbits aren't perfect circles, they're ellipses, slightly stretched circles. So planets speed up when they're closer to the Sun, slow down when they're farther away. But the changes are gradual, smooth. Earth is closest to the Sun in early January, about 147 million kilometers away. Farthest in early July, about 152 million. You'd never notice the difference. The Sun looks the same size all year. But Earth knows. It speeds up slightly in January, slows slightly in July. A gentle ebb and flow, like breathing. In and out, closer and farther, faster and slower, all in silence. And this will continue for billions of years. The Sun will eventually die, swell into a red giant, possibly consume Earth. But until then, the orbit continues, reliable, steady, peaceful. 365.25 days, again and again. No sound, no fanfare, just motion, pure and simple. Moons and their tidal embrace. Moons don't just orbit, they pull. Every moon exerts a gravitational force on its planet, and the planet pulls back. This creates tides. On Earth, our moon is responsible for ocean tides. As the moon orbits, its gravity pulls on the water. The oceans bulge slightly toward the moon, and also on the opposite side due to centrifugal force. As Earth rotates beneath these bulges, we experience high tide and low tide, twice a day. But the moon doesn't just pull on the oceans, it pulls on the entire planet. The solid ground rises and falls too, by about 30 centimeters. You don't feel it, but it's happening. Right now, the ground beneath you is gently moving up and down, breathing with the moon's pull. And the moon? It's slowly drifting away, about 3.8 centimeters per year. Because of tidal forces, Earth's rotation is slowing down, just a tiny bit. And as it slows, the moon moves farther away. It's been happening for billions of years. When the moon first formed, about 4.5 billion years ago, it was much closer, maybe 10 times closer than it is now. Back then, a day on Earth was only about 6 hours long. The moon loomed huge in the sky. Tides were enormous. But over time, things have settled, calmed, slowed down. Now, a day is 24 hours. The moon is farther away. Tides are gentler. And the process continues, slowly, patiently. In another billion years, days will be slightly longer. The moon will be slightly farther. But the change is so gradual, you'd never notice in a lifetime. Just like the orbit itself, the moon's drift is silent, peaceful, inevitable. Other moons experience similar dynamics. Io, one of Jupiter's moons, is caught in a tidal tug of war. Jupiter pulls on one side, Europa and Ganymede, two other moons, pull from other directions. This constant squeezing and stretching generates heat, enough heat to power hundreds of volcanoes on Io's surface. But Io's orbit, still smooth, still silent. Despite the volcanic chaos on its surface, Io glides through space, every 42.5 hours, around and around. No sound, just motion, and gravity's gentle, relentless pull. Enceladus, a moon of Saturn, has geysers. Water erupts from cracks in its icy surface, shooting hundreds of kilometers into space. And why? Tidal heating. Saturn's gravity squeezes Enceladus, generates warmth, melts subsurface ice. The geysers are dramatic, but the orbit, calm, quiet. Enceladus circles Saturn every 33 hours, silently, while water escapes into space, forming part of Saturn's E-ring. All of it happening without a whisper.
Asteroid belts. A slow river of rock. Between Mars and Jupiter lies the asteroid belt. Millions of rocky fragments, ranging from tiny pebbles to dwarf planets hundreds of kilometers across. And they're all drifting, slowly, orbiting the sun. But despite what movies might show, the asteroid belt is not crowded. If you were flying through it in a spacecraft, you'd likely see nothing, just empty space. The asteroids are spread out, millions of kilometers apart on average. You could fly through the belt and never come close to a single rock. But they're there, billions of them, each on its own path. Some asteroids take 3 years to orbit the sun, some take 6, some take longer. They drift, slowly, silently. Occasionally, 2 asteroids collide. When they do, they shatter, creating smaller fragments. But these collisions are rare, and when they happen, they're silent. No crash, no boom. Just 2 rocks touching, breaking apart, drifting away as smaller pieces. Over billions of years, the asteroid belt has been grinding itself down. Collisions create dust. Dust drifts away. Some falls into the sun. Some escapes the solar system. But the process is slow, patient. The asteroid belt is quieter now than it was 4 billion years ago. Fewer collisions, more empty space. One day, billions of years from now, it might be almost empty. Just a few lone rocks drifting in the space between Mars and Jupiter. But for now, it's still there, a river of stone, flowing silently around the sun. And within that belt, some asteroids have their own moons, tiny companions, orbiting even tinier worlds. One asteroid, Ida, has a moon called Dactyl, just 1.4 kilometers across. Dactyl orbits Ida silently, slowly, a miniature version of the Earth-Moon system. 2 mocks bound by gravity, drifting through space together. No sound, no drama, just companionship, quiet and eternal. Comets, patience on an elliptical path. Comets are wanderers. They come from the far reaches of the solar system, the Kuiper belt, the Oort cloud, regions so distant, so cold that even the sun's light is faint. And they orbit, but not in neat circles like planets. Comets follow long, stretched ellipses, looping far out into space, then swinging close to the sun. Some comets take just a few years to complete an orbit. Halley's Comet, for example, returns every 76 years. Others take thousands, millions. The comet Hale-Bopp, which passed Earth in 1997, won't return for another 2,500 years. And some comets are on their first visit, coming from the Oort cloud, 1 trillion kilometers away, taking millions of years to fall inward. They drift silently for eons, frozen, inactive. But as they approach the sun, something changes. The ice begins to warm, slowly, gently. Water, carbon dioxide, and other frozen gases start to sublimate, turn directly from solid to gas. And as they do, they form a cloud round the comet, a coma, glowing softly in the sunlight. The solar wind, a stream of charged particles from the sun, pushes on this gas, creating a tail. Long, flowing, beautiful, but silent. A comet's tail can stretch for millions of kilometers, but it makes no sound. It's just gas and dust drifting away from the comet, pushed gently by sunlight and solar wind. And as the comet swings around the sun, it begins its long journey back out, into the cold, into the dark. The tail fades, the coma dissipates, the comet freezes again.
and it drifts, silently, back to the outer reaches of the solar system, where it will wait for decades, centuries, millennia, until gravity pulls it inward again and the cycle repeats. Comets are among the most patient travelers in the solar system. They don't rush, they don't hurry. They simply follow their paths, silently, gracefully. And when they pass by Earth, we look up, we marvel, we call them omens, harringers, wonders. But the comet doesn't care. It's just passing through, on its long, quiet journey. No sound, no announcement. Just ice, rock, and gravity, drifting through the cosmos.
The expansion of space, the gentlest push. Now, let's zoom out, far out, beyond our solar system, beyond our galaxy, to the largest scale. The universe itself is expanding, not into something. There's no outside for it to expand into. Space itself is growing. The distance between galaxies is increasing, and it's happening everywhere, all at once. Right now, distant galaxies are moving away from us, not because they're traveling through space, but because the space between us and them is expanding. The farther away a galaxy is, the faster it appears to recede. Some galaxies are so far away that the space between us is expanding faster than the speed of light. Does that violate relativity? No, because they're not moving through space. Space itself is expanding. And we'll never see those galaxies. Their light will never reach us. The expansion is too fast. But closer galaxies, we can see them, and we can measure how fast they're moving away. This is called redshift. As space expands, the wavelengths of light stretch, shift toward the red end of the spectrum. The more red-shifted a galaxy is, the farther away it is, and the faster it's receding. This expansion has been happening for 13.8 billion years, since the Big Bang, and it's accelerating, driven by something we call dark energy. We don't know what it is, we just know it's there, pushing space apart, gently, relentlessly. One day, trillions of years from now, the universe will be so spread out that galaxies will be isolated, alone. From any one galaxy, you won't be able to see any others. The space between them will be too vast, expanding too quickly. Each galaxy will be an island in an ocean of darkness. But that's far in the future. For now, the expansion is slow enough that we can still see billions of galaxies, still map the cosmic web, still witness the universe in all its connected glory. And the expansion itself? Silent. Space doesn't make noise as it stretches. Galaxies don't whoosh as they drift apart. It's the quietest, gentlest force in the universe. An invisible hand slowly pushing everything away from everything else. Patient, inexorable, peaceful. Dark energy, the invisible hand. We don't understand dark energy. We know it exists because we can measure its effects, but we don't know what it is. It makes up about 68% of the universe, more than anything else. Dark matter makes up 27%. Normal matter, stars, planets, you, me, just 5%. So the universe is mostly unknown. Dark energy is even stranger than dark matter. Dark matter at least behaves like matter. It has gravity, it clumps together, it helps form galaxies. But dark energy? It does the opposite. It pushes, repels, drives things apart. And the more space there is, the more dark energy there is, because it's a property of space itself. As the universe expands, more space is created, and with it, more dark energy, which causes the expansion to accelerate. It's a runaway process. The more space, the more dark energy. The more dark energy, the faster the expansion. The faster the expansion, the more space. But it's happening slowly, over billions of years.
Right now, the acceleration is gentle, barely noticeable on human timescales, but over cosmic timescales, it's everything. Dark energy is why distant galaxies are speeding away, why the universe's expansion is accelerating, why one day the cosmos will be cold, dark, and empty. But we don't hear it, we don't see it directly. We only see its effects, the stretching of space, the redshift of distant light. Dark energy is the universe's quietest force, and its most powerful. An invisible hand, gently, patiently, pushing the universe apart, forever. Lagrange points, where gravity finds balance. There are places in space where gravity balances perfectly, called Lagrange points. Imagine two massive objects, the Earth and the Moon, for example. Their gravitational fields interact, and at certain points in space, the pull from Earth and the pull from the Moon cancel out. Not completely, but enough that an object placed there will stay there relative to Earth and the Moon. There are 5 Lagrange points in the Earth-Moon system. L1 is between Earth and the Moon. An object there feels equal pull from both. L2 is on the far side of the Moon, useful for satellites that need to stay in the Moon's shadow. L3 is on the opposite side of Earth from the Moon. L4 and L5 are ahead of and behind the Moon in its orbit, forming equilateral triangles with Earth and the Moon. L4 and L5 are special. They're stable. Objects naturally collect there. In the Sun-Jupiter system, L4 and L5 are full of asteroids, called Trojan asteroids. Thousands of them, drifting in these gravitational sweet spots, not orbiting Jupiter, not orbiting the Sun independently, just sitting there, balanced. Humanity has placed satellites at Earth's Lagrange points. The James Webb Telescope sits at L2, about 1.5 million kilometers from Earth. There it orbits not Earth, not the Sun, but the L2 point itself. It's a delicate balance. The satellite has to make small adjustments, tiny thruster burns, but mostly it just drifts, held in place by the combined gravity of Earth and Sun. Silent, stable, peaceful. Lagrange points remind us, even in the chaos of gravitational forces, there are pockets of stillness, places where everything balances, where motion becomes rest. And there, in those quiet points, things can simply be.
Europa's ice, layers accumulating over eons. Jupiter has a moon called Europa. From a distance, it looks smooth, almost perfectly white, like a billiard ball made of ice. But look closer, and you'll see cracks, lines, ridges, patterns etched across the surface. Europa is covered in ice, a thick shell, perhaps 15 to 25 kilometers deep. And beneath that ice, an ocean, liquid water, possibly 100 kilometers deep. More water than all of Earth's oceans combined. The ice on Europa's surface is ancient, formed over billions of years, but it's not static, it's slowly changing. The moon is tidally heated. Jupiter's immense gravity squeezes Europa as it orbits. This generates warmth, enough to keep the subsurface ocean liquid. And that warmth causes the ice to shift, crack, refreeze. New ice forms from below. Water seeps up through cracks, freezes on the surface. Over millions of years, the ice shell is renewed, layer by layer. It's a slow process, imperceptibly slow. If you stood on Europa's surface, you wouldn't see anything moving. The ice would look still, frozen, eternal. But over thousands of years, cracks would widen, shift, new ridges would form. Over millions of years, the entire surface would be reshaped. Scientists believe Europa's surface is relatively young, perhaps only 40 to 90 million years old. That sounds ancient, but in cosmic terms, it's recent. The ice is constantly being recycled. Old ice sinks, new ice rises. And in that slow churning, there's a kind of life, a kind of breathing. Europa's ocean beneath might harbor life,
Microbes, perhaps, living in the dark, fed by hydrothermal vents on the ocean floor. We don't know, but it's possible. And if life exists there, it would know nothing but darkness and cold and slow, patient change. Ice forming above, water flowing below, all of it happening over timescales longer than civilizations. Europa's ice is a reminder the universe transforms, but slowly, layer by layer, molecule by molecule. There's no rush, just the steady accumulation of frozen water over eons. Quiet, patient, beautiful.
Impact craters, stories written in stone. Look at the moon. Even from Earth, you can see dark patches. Those are Maria, large flat plains formed by ancient lava flows. And scattered across the surface, craters, thousands of them. Each one tells a story. Billions of years ago, the solar system was chaotic. Asteroids and comets flew everywhere. Collisions were common. The moon, with no atmosphere to protect it, was bombarded. Every impact left a mark, a crater. Small asteroids made small craters. Large ones made large craters. Some impacts were so massive they cracked the moon's crust. Lava welled up, filling the basins, creating the Maria. And then, over time, the bombardment slowed. Fewer asteroids, fewer comets, fewer impacts. The moon's surface stabilized. The craters remained, unchanged. And because the moon has no atmosphere, no wind, no water, those craters have stayed almost exactly as they were, for billions of years. The footprints left by Apollo astronauts in 1969, still there, perfectly preserved, because nothing disturbs them. No wind, no rain, just the slow, patient accumulation of micrometeorite dust. Eventually, millions of years from now, those footprints will be buried, covered by dust. But the craters? They'll remain for billions more years. Craters are the universe's way of keeping time. On Earth, craters erode. Wind, water, and tectonic activity erase them. Even the largest impact craters are eventually worn away. But on airless worlds, the Moon, Mercury, asteroids, craters last. Each one a timestamp, a record of when an object struck. Scientists can look at the Moon's surface and estimate its age by counting craters. More craters, older surface. Fewer craters, younger surface. Europa, with its smooth, crack-covered ice, has very few craters because the surface is constantly being renewed. But the Moon? Covered, ancient, untouched. And those craters were formed in silence. No sound, just an asteroid falling through space, striking the surface, vaporizing, leaving a scar. And that scar remains, a quiet monument to a moment of violence billions of years ago. There's something peaceful about that permanence, isn't there? The universe remembers, even when there's no one to witness, even when eons pass. The craters remain, patient, enduring, waiting to tell their stories to anyone who looks closely enough. Mountains on Titan, rising in a hazy atmosphere. Saturn has a moon called Titan. It's the only moon in the solar system with a thick atmosphere, thicker than Earth's, in fact, made mostly of nitrogen, with methane clouds and a hazy orange sky. On Titan's surface, it's cold, minus 179 degrees Celsius, so cold that water ice is as hard as rock, and methane, which on Earth is a gas, exists as liquid. Lakes and rivers of liquid methane flow across Titan's surface. It rains methane. Methane evaporates, a hydrocarbon cycle like Earth's water cycle, but much colder, much stranger. And on Titan, there are mountains, not made of rock, made of water ice, frozen solid,
harder than stone in that cold. These mountains rise slowly over millions of years. How? Titan has cryovolcanoes, volcanoes that erupt not with lava, but with liquid water and ammonia. When they erupt, rarely, slowly, they deposit ice, layer by layer. Over time, these deposits build up, form hills, mountains. It's a process similar to how mountains form on Earth, but much slower, much colder. Titan's mountains are not dramatic, not towering peaks like the Himalayas. They're gentle, rounded, worn smooth by methane rain and wind. But they're there, rising, slowly. One day, perhaps millions of years from now, new mountains will have formed. Old ones will have eroded away. But the process is so slow you'd never see it happen. Even over a human lifetime, even over 1,000 human lifetimes, just slow, patient geological change in a world of methane lakes and icy mountains. Titan is a reminder that even on the strangest worlds, familiar processes happen. Erosion, deposition, mountain building, just slower, quieter, in conditions we can barely imagine. But it's happening, right now. Ice accumulating, methane flowing, mountains rising, all in silence, all with patience. Dust settling on Mars, a surface undisturbed. Mars is covered in dust, fine reddish dust, made of iron oxide, rust. It covers the entire planet, the plains, the mountains, the polar ice caps, and it's been accumulating for billions of years. Every now and then, a dust storm sweeps across Mars. Sometimes these storms are global, covering the entire planet in a haze that lasts for months. But most of the time, Mars is calm. The dust settles, slowly, gently. On Earth, dust doesn't last long. Wind blows it away, rain washes it off, vegetation grows over it. But on Mars, there's no rain, no vegetation, just thin air and weak winds. So dust accumulates, layer by layer. NASA's rovers have left tracks on Mars, tire marks, footprints from robot wheels, and those tracks remain for years, decades, maybe centuries, because nothing disturbs them. Eventually, a dust storm might cover them, or new dust might slowly bury them, but for now, they're there, visible from orbit, a record of humanity's brief visit to another world. Mars has rocks covered in dust. Some have been sitting untouched for millions of years. The rovers brush off the dust, reveal the rock beneath, and scientists study it, learning about Mars's past. But the dust? It's part of Mars's story too. Each layer a chapter, a record of time. Some dust is ancient, formed when Mars had a thicker atmosphere, when water flowed on its surface. Some is recent, formed from wind-blown sand and eroded rock, and all of it slowly settling, accumulating, covering the planet in a soft reddish blanket. One day, millions of years from now, Mars might look different, more dust, thicker layers. Or perhaps, if humanity ever terraforms Mars, the dust will be swept away by rain, by rivers, by life. But for now, it settles, patiently, quietly, grain by grain, year by year. No rush, no urgency, just dust falling gently on a planet that has all the time in the world.
The slow death of red giants, stars shedding their layers. Stars don't die quickly, not most of them anyway. Some massive stars explode, supernovae, brilliant, violent, fast. But smaller stars like our Sun, they die slowly, gently, over millions of years. When a star like the Sun exhausts its hydrogen fuel, it begins to change. The core contracts, heats up, starts fusing helium, and the outer layers expand. The star swells, becomes a red giant. It grows larger, cooler on the surface, but brighter overall. Our sun will do this in about 5 billion years. It will swell to the orbit of Venus, maybe even Earth. And it will stay that way for millions of years, slowly burning helium, slowly expanding. And then the outer layers begin to drift away. Not explosively, gently. The star sheds its atmosphere, layer by layer, a slow, stellar wind. Those layers form a cloud around the star, a planetary nebula. Glowing gas, lit by the hot core at the center. Beautiful, delicate, ephemeral. But the process takes thousands of years. The gas drifts outward, slowly, expanding, dimming. Eventually, the nebula fades, disperses into space. And what remains is the core, a white dwarf. Hot, dense, no longer fusing anything, just radiating leftover heat. And it cools over billions of years. The death of a star like the sun is not dramatic, it's patient, gradual. A slow shedding, a gentle fade. Like a fire burning down to embers, then cooling slowly over eons. And the material the star sheds, that gas, that dust, drifts into space. Eventually, it becomes part of new stars, new planets, new life. The star dies, but its atoms endure, recycled, reborn. Slowly, patiently, in the universe's endless cycle. Erosion on asteroids, weathering without weather. On Earth, erosion is constant. Wind, water, ice, all of them wearing down mountains, carving valleys, shaping the land. But in space, there's no wind, no water, no ice flows. So how do things erode? Slowly, very slowly. Asteroids are bombarded by tiny particles, micrometeoroids, dust grains traveling at thousands of kilometers per hour. When they strike an asteroid, they chip away tiny fragments. Over millions of years, this smooths the surface, wears down sharp edges. It's called space weathering. An asteroid starts out rough, angular, fresh. But over time, impacts smooth it, dust accumulates, the surface darkens. It's a slow process, incredibly slow, but it's measurable. Scientists can look at an asteroid and estimate how long it's been exposed to space by how weathered it looks. More weathered, older. Less weathered, younger, perhaps recently fractured from a larger body. And this erosion happens in silence. No wind whistling, no water rushing, just tiny impacts over and over for millions of years. Grain by grain, the surface changes. Some asteroids have been in space for billions of years, almost as old as the solar system itself. Their surfaces are ancient, worn, smooth. A record of time, written in dust and tiny craters. And the process continues, right now, on every asteroid, every moon, every rock in space, slowly, patiently, worn down by the universe's gentlest erosion.
Tidal locking, when rotation stops. Many moons are tidally locked. What does that mean? It means they always show the same face to their planet. Our moon is tidally locked to Earth. The same side always faces us, the near side. The other side, the far side, we never see from Earth. Not because it's dark, just because it's always facing away. How did this happen? Tidal forces. Billions of years ago, the moon rotated faster. It had its own day-night cycle. But Earth's gravity pulled on the moon, creating tidal bulges. Those bulges acted like a brake, slowing the moon's rotation. Over millions of years, the moon slowed down, until eventually its rotation matched its orbit. Now, one side always faces Earth. The moon rotates once every 27.3 days, and it orbits Earth in the same time, perfectly synchronized. And it will stay that way for billions of years. This process, tidal locking, happens to most moons. Io, Europa, Ganymede, Callisto, all tidally locked to Jupiter. Titan, tidally locked to Saturn. Charon, tidally locked to Pluto. And Pluto is tidally locked to Charon. They always show the same faces to each other. It's a slow process, taking millions of years, but once it's complete, it's stable, permanent, a kind of cosmic stillness where rotation and orbit become one. There's something peaceful about that, isn't there? No more spinning, just a steady orbit, always facing the same direction. A moon forever gazing at its planet, and the planet forever seeing the same face. A quiet bond, a gravitational embrace that will last for eons.
The wisdom of starlight. Distance is not absence. Remember the photon we talked about in the first chapter? Born in a star's core, taking thousands of years just to reach the surface, then traveling through space for years, decades, even millennia, and finally landing softly on your skin, in your eyes. That journey teaches us something profound. Distance doesn't mean absence. Separation doesn't mean disconnection. That star might be hundreds of light years away, or thousands, or millions, but its light reaches you, touches you, connects you. Right now, you're being touched by countless stars, their ancient light finally arriving, gently landing. And in the same way, the people you love, even when they're far away, even when you can't see them, are still connected to you. Distance is just space, not absence. The light still travels, the connection endures, patiently, quietly, across whatever distance separates you. The universe doesn't let distance break bonds. It just makes the reunion more precious. Every photon that completes its journey is a small miracle, a reminder that even across vast emptiness, connection persists. And so it is with us. We are never truly alone, never truly separate. We're all made of stardust, all connected by invisible threads of gravity, light, and shared origin. The universe holds us, gently, even when we feel isolated. The light still reaches us, always. The wisdom of galaxies. Slow transformation is still transformation. We watched galaxies merge, two massive spirals drifting toward each other over hundreds of millions of years, so slowly that in a human lifetime you'd see no change at all. But the change is happening, real, inevitable. And this teaches us patience with ourselves. You might feel like you're not changing, not growing, not progressing, but you are. Just like galaxies, your transformation is slow, gradual, imperceptible day to day. But over years, over a lifetime, the change is profound. You're not the same person you were 5 years ago, 10 years ago, 20. You've merged with experiences, with people, with knowledge, and you've become something new, something richer, something more complete. The process isn't finished. It never is. Galaxies continue merging, stars continue forming, the cosmic dance continues, and so do you, continuing, evolving, slowly, beautifully. Don't be frustrated by the pace. Don't wish for sudden transformation. The universe doesn't work that way, and neither do you. Trust the slow process. Trust the patient unfolding. You're exactly where you need to be right now, moving forward, even if you can't see it, even if it feels like nothing is changing.
You are, slowly, surely, like galaxies spinning through space.
The wisdom of patience. The best things unfold slowly. Ice accumulating on Europa, craters forming on the moon, mountains rising on Titan. All of these transformations take millions of years, and they remind us the best things unfold slowly. We live in a world of instant gratification, fast food, fast internet, fast everything. But the universe doesn't do fast. Stars take millions of years to form. Planets take billions. Life evolved over eons. And the result? Beauty, complexity, wonder. Rushing produces poor results. Patience produces masterpieces. Your growth, your healing, your dreams, they take time. And that's okay. That's natural. Don't be frustrated by the pace. Don't feel like you're behind. The universe itself has taken 13.8 billion years to get to this moment, and it's not finished. Neither are you. And that's not a flaw. That's the design. You're unfolding, slowly, beautifully. Trust the process. Trust the timeline. The universe has time, and so do you. More than you think. You are made of stars, a connection that never breaks. Carl Sagan said it best. We are made of star stuff. Every atom in your body was forged in a star. The calcium in your bones, the iron in your blood, the oxygen you breathe. All of it came from stars that lived billions of years ago. Stars that died, exploded, scattered their elements into space. And those elements drifted for millions of years through nebulae, through clouds of gas and dust, until they came together, formed the sun, formed Earth, formed you. You are not separate from the universe. You are the universe, experiencing itself, knowing itself. When you look at the stars, you're not looking at something distant and foreign. You're looking at your ancestors, your origins, your family. The universe is not out there. It's in you. You're part of it. And that connection can never be broken. Even when you feel small, even when you feel lost, you're part of something vast, something ancient, something beautiful. The stars are in you, and you are in the stars, forever connected, forever home. And now it's time to rest. Throughout this journey, we've explored the universe's quiet wonders, its patient rhythms, its gentle transformations. And now it's time to join that rhythm, to let go, to rest. The universe will continue without you tonight, and that's okay. Stars will keep shining, galaxies will keep spinning, planets will keep orbiting. The cosmic dance will continue, patient, steady, eternal. And you can rest deeply, peacefully. You don't need to hold everything together. You don't need to stay vigilant. The universe has been doing this for billions of years. It knows what it's doing. You can trust it. You can let go. Close your eyes, if they're not already closed. Feel your breath, slow, steady, in, out, like the expansion and contraction of space, like the rhythm of the cosmos. You're part of that rhythm now, breathing with the universe. Let your thoughts drift, like cosmic dust, gently floating, settling. No need to hold on to them. Let them go. Let your body relax completely, every muscle, every tension, sinking into softness, into comfort. The universe is holding you gently, like gravity holds planets. You're safe, you're supported. And as you drift towards sleep, know this:
You've been on a beautiful journey tonight, through light and darkness, through sound and silence, through time and space. And tomorrow, the journey continues, but differently. Tomorrow you'll wake, and the universe will still be here, patient, beautiful, waiting. But tonight you rest, in the quiet, in the peace, in the gentle embrace of cosmic stillness. Thank you for joining me on this journey, through starlight and galaxies, through faint glows and silent motion, through slow transformations and cosmic patience. We've explored the universe's quiet wonders together, and I hope you found some peace, some comfort, some gentle wisdom. Remember, you're made of stars. You're connected to everything. You don't need to rush. You don't need to shine brightly. You're exactly enough, exactly as you are. And the universe, it will continue, patient, beautiful, eternal, spinning its galaxies, drifting its planets, glowing its faint lights, all in silence, all with peace. And you're part of that forever. So rest now, deeply, peacefully. Let the universe hold you. Let the darkness comfort you. Let sleep come gently. Good night, cosmic traveler. You are stardust. You are the universe. You are enough. Sleep well. The stars will still be there tomorrow, and so will you.